As developers, we often work with data that needs to be stored and retrieved efficiently. Whether it's user information, product catalogs, or sensor readings, the ability to persist data is crucial for building robust and dynamic applications. This is where databases come into play. Databases provide a structured and organized way to store, manage, and retrieve data, enabling us to build powerful and data-driven applications. Imagine building a web application without a database. Every time a user closes the application, their data would be lost. This is not ideal. Databases provide a persistent storage mechanism that allows our applications to remember information even after they are closed and reopened. This persistence is essential for creating applications that are useful and reliable. Without databases, we would be limited to storing data in temporary structures like variables, which would disappear once the program terminates. Databases free us from these limitations, allowing us to focus on building the logic and functionality of our applications. In the realm of databases, there are various options available, each with its own strengths and use cases. Some popular choices include MySQL, PostgreSQL, and MongoDB. These databases are powerful and widely used. However, they often require setting up a separate server and can be an overkill for smaller projects or when you need a simple local data store. This is where SQLite shines. SQLite is a lightweight, serverless, and self-contained database engine that is perfect for local data storage and Python applications. It's fast, easy to use, and doesn't require complex configuration, making it an excellent choice for beginners and experienced developers alike. SQLite is a fantastic choice for developers who need a lightweight and efficient way to store data locally within their Python applications. Unlike client-server database systems that require a separate server process, SQLite operates directly on files. This means you don't have to worry about complex setup procedures or managing a separate database server. You can simply embed SQLite within your Python application, and it takes care of all the database management tasks behind the scenes. One of the key advantages of SQLite is its portability. Since it operates on files, you can easily move your database between different systems by simply copying the database file. This makes it incredibly convenient for developing applications that need to run on multiple platforms without worrying about database compatibility issues. Additionally, SQLite is highly self-contained. It doesn't have any external dependencies, meaning you don't need to install any additional libraries or software to start using it in your Python projects. SQLite is not just easy to use, it's also incredibly powerful. It supports a significant subset of the SQL standard, allowing you to perform various database operations like creating tables, inserting data, querying data, and much more. Don't let its lightweight nature fool you. SQLite is more than capable of handling data management tasks for a wide range of applications, from small desktop tools to mobile apps. Python comes equipped with built-in support for SQLite through the module. This module provides a simple and intuitive interface for interacting with SQLite databases directly from your Python code. To start working with SQLite, you don't need to install any additional libraries. Simply import the module, and you're ready to go. To connect to an SQLite database, you use the function from the module. This function takes the database file name as an argument. If the file doesn't exist, it will be created automatically. Once you have the connection object, you can start interacting with the database. Import SQLite 3. In this code, we first import the module. Then, we establish a connection to our database, which is named, mydatabase.dbe. If this file doesn't exist in the current directory, SQLite will create it automatically. The function returns a connection object, which we store in the variable. Next, we create a cursor object. Think of the cursor as a handle that allows us to execute SQL commands and fetch results from the database. It's like a pointer that indicates our current position within the database. With the cursor ready, we can now execute SQL commands to create tables, insert data, or retrieve information. After executing our SQL commands, it's essential to commit the changes we've made. This ensures that any modifications we've done to the database are saved permanently. Finally, we close the connection to the database. It's good practice to close the connection when you're done with your database operations to release resources and prevent potential issues. Tables are the foundation of any relational database, and SQLite is no exception. Tables provide a structured way to organize your data into rows and columns, much like spreadsheets. Each row in a table represents a single record, while each column represents a specific attribute or field associated with that record. Before you can start storing data in your SQLite database, you need to create tables to hold that data. To create a table, you use the statement followed by the table name and a list of column definitions enclosed in parentheses. Each column definition specifies the column name, data type, and any constraints you want to apply to that column. Create table users, ID integer, primary key auto increment, name text, not null, email text, unique. In this example, we're creating a table named users with 3 columns, ID, name, and email. The ID column is an integer and is designated as the primary key. The keyword ensures that each new user added to the table automatically gets a unique ID. The name column is defined as and cannot be empty, ensuring that every user has a name. Lastly, the email column is also a field with a constraint, meaning no 2 users can have the same email address. Section 5. Populating your database. Inserting data with SQL. Once you have your tables set up, you can start populating them with data. The statement in SQL allows you to add new records into your tables. This statement specifies the table you want to insert data into and the values for each column. You can insert data for all columns or specific columns depending on your needs. SQL insert into users, name, email, values, John Doe, John.Doe at example.com, Jane Smith, Jane.Smith at example.com. In this case, we're inserting 2 new records into the users table. We're providing values for the name and email columns, while the ID column, being an auto-incrementing primary key, will be automatically assigned unique values by SQLite. Section 6. Updating existing data, keeping information current. Data in databases is rarely static. As your application evolves and requirements change, you'll often need to update existing records in your tables. SQL provides the statement for this purpose, allowing you to modify the values of specific columns in existing rows based on certain conditions. SQL update users set email =, john.doe.updated at example.com, where name =, John Doe. This SQL statement updates the email address of the user named John Doe in the users table. The clause specifies the column to update and the new value, while the clause identifies the specific row to modify. In this example, we're updating the email address to john.doe.updated at example.com, only for the user whose name is John Doe. The clause ensures that we're modifying the correct record. Section 7. Fetching data with queries, retrieving valuable information. Storing data is only one part of the equation. The real power of databases lies in their ability to retrieve specific information efficiently. SQL provides the statement, which is the cornerstone of data retrieval in relational databases. With, you can specify the columns you want to retrieve data from, the tables you want to access, and any conditions that the data must satisfy. Select asterisk from users where name =, Jane Smith. This query selects all columns from the users table where the name column is equal to Jane Smith. This will return all information stored in the table for the user named Jane Smith. The statement is incredibly versatile, allowing you to perform complex filtering, sorting, and aggregation operations on your data. Section 8. Putting it all together. Building a simple task list application. Let's bring everything together and build a simple task list application using SQLite and Python. In this application, users will be able to add new tasks to their list, mark tasks as completed, and view their pending tasks. Import SQLite 3, create table if not exists. Tasks, ID integer, primary, key auto increment, task text not null, completed integer default 0. Cursor, execute, insert into tasks, task, values, task, con.com, might, print, task added successfully, cursor. Execute, update tasks, set completed =1, where ID =, task _ID, con.com, mit, print, task marked as completed, cursor. Execute, select asterisk from tasks where completed =0, pending _tasks, =cursor.fetchAll, if pending _tasks, print, pending tasks, for task in pending _tasks, print, f, task 1, ID, task 0, else, print, no pending tasks. Hash example usage, add task, learn SQLite, add task, build a task list app, complete _task, 1, view, _pending _tasks. #close the connection con.close. In this code, we define functions to add tasks, mark them as completed, and view pending tasks. The application connects to an SQLite database and creates a table named tasks if it doesn't already exist. Each task has an ID, description, and a flag to indicate whether it's completed. Users can interact with the application through these functions to manage their tasks. Section 9. Visualizing data schemas and result sets. Visualizing data can greatly enhance our understanding of how information is structured and stored within our database. When we talk about visualizing data in the context of SQLite, we often refer to two key aspects: database schemas and result sets. Database schema. A database schema is a high-level description of your database structure. It outlines the tables in your database, the columns within each table, and the relationships between those tables. Think of it as a blueprint that shows how your data is organized. Visualizing the schema can be incredibly helpful, especially when you're working with multiple tables and complex relationships. Result sets. When you execute SQL queries to retrieve data from your database, the results are typically returned in a tabular format known as a result set. This result set is essentially a table that contains the data that matches your query criteria. Visualizing result sets can make it easier to interpret the retrieved data. Section 10. Conclusion: empowering your Python applications with SQLite. In this essay, we've delved into the world of SQLite and how it can be seamlessly integrated with Python to provide persistent data storage for your applications. We've covered the fundamentals of connecting to SQLite databases, creating tables to structure your data, inserting and updating records, and retrieving data using SQL queries. Understanding how to work with SQLite empowers you to build a wide range of applications that require local data persistence. Whether you're developing a simple desktop tool to manage your to-do list, or a more complex application that requires data storage and retrieval, SQLite provides a lightweight and efficient solution. By incorporating SQLite into your Python projects,